before I do that. Yes. And I just get a competition. I just get a difference between the scale, K, and that Jinx length, that Jinx Fourier mode. Okay? Does rho, yes, rho bar appears here. So this is rho bar. Everywhere should be a bar. Rho bar appears here times delta. Okay? And just now, depending, you see that this defines this important scale that will be at the heart of our suppression here. Depending on whether k is greater than kj or smaller than this kj, the equations will be different. So you see that for k much greater than kj, so if this guy is negligible, what I get is this, so this is a double dot. What I get is just a harmonic oscillator equation with a pressure, with a frequency given by the c squared times k squared. So for k greater than kj, I just get delta double dot plus 2h delta dot plus cs squared k squared delta is equal to 0. So this is a damped, and the damped is important also, harmonic oscillator. And in the opposite limit, I just get a growth equation. I just get delta double dot plus 2h delta dot minus 4 pi j. And I guess, yeah, I think in my notes I forgot an a square. Rho delta equal to 0. Sorry. Okay. So this is just a growth equation. And we can solve these equations. Obviously, this is going to be, you know, an oscillatory pattern times some damping function in front. And this is going to be this is going to give me growth equation. So a solution where delta grow with the scale factor. So this equation at the bottom is valid, for instance, for dark matter at all times, because the sound speed of dark matter is 0. For neutrinos, the sound speed is not 0, so there's going to be this competition between the two. But you can also apply it to the photon baryon fluid, for instance. I mentioned to you the sound speed of the photon baryon fluid. You can look, you can do exactly the same game, and you'll see that here you'd find here the sound speed of this photon baryon fluid to be this c over square root of 3 I gave you earlier. So this is really the same equation applies for basically every species, as long as we take this approximation, which is sigma goes to 0. So when we solve this equation, what we see, yes, I have to erase now. So let's just, so importantly, let us focus on this in the limit where k is much smaller than kj. So on large, small k means on large scales. What we find, so we can, this is a second order linear ODE, order linear ordinary differential equation. So this has a simple, the form of the solution is very simple. Is equal to some initial condition. So delta k, this is something that depends on k, which is the initial condition, time a growth function with that only depends on time, plus the same thing, but with but now instead of a growth, it's a decaying function basically. And this decaying mode I'm going to ignore. This I'm not going to, sorry, it's not equal to 0, but I'm just ignoring because it decays literally. So perturbations are not, this part of the solution we don't see. What we see of the solution is this part. And when we plug this ansatz, we can then solve, and we get that the important thing is what makes it a little hard to analytically solve is just that H can be complicated, can have a non-analytic, expression, when you want to solve for it. So what we do is we take limits, we take H dominated by radiation, then we have some polynomial form for A, simplifies everything, or for the matter, or when H is dominated by matter. So in the radiation dominated era, what we find is that D plus, is what I was telling you yesterday. I should write as a function of what? So I'm a little bit sloppy again between between A and time. I apologize for that. Let me do something that's bad, but I'm going to write everything in terms of A now. We find that this function is proportional to the logarithm of the scale factor. Okay? So basically what it means is that modes delta k's, that's what we mean by a mode, is this equation is valid for each k. For each k value, you have an infinite series of equations. And for modes k that enter the horizon, which means k, we compare k with respect to 1 over the length scale associated with the Hubble ray. Sorry, actually, I should be careful a second whether that's the... Yeah, it's going to be this. We compare k with respect to AH. If you're within the horizon, basically, you're going to start growing with the logarithm of A. So large scales start, large k, small scales start to grow in the radiation-dominated era. And then in the matter-dominated era, the solution of this equation proportional to A. So this is a very famous result that can be derived, taking a little bit of time to find these solutions, but that tells us that unless you're matter-dominated, perturbations almost don't grow. Okay? And dark matter perturbation. Now let's just look at what, for a second, let's look at what dark matter perturbation would look like. And then we'll do neutrinos to compare. So for dark matter, CS square is equal to 0. So this growth equation is always valid at all scales for dark matter. So that means that if I do two different modes, k of, I don't know, 0.01, what did I say? Sorry, let me see. 0.001. I should be a little bit careful because I want it to enter the horizon. So let me take 0.01, sorry. And k equal 1 megaparsec inverse. I'm going to draw their evolution with respect to A. What this solution tells me is just that it's the initial condition. So let's put AEQ, which is simply defined as is the matter radiation equality scale factor. So it's omega radiation over omega matter. Yesterday we had defined redshift of equality, which was the inverse of that relation. Which is something like 10 to the minus 4, a few times 10 to the minus 4. So the first mode to enter is going to be this guy. So this guy enters a little bit, so it's stuck at his initial conditions, if you wish, and then it enters and it starts growing like the logarithm of A. So this is the moment where K is order AH. Grow like the logarithm of A, and here we reach AEQ, and you grow like A. Okay? And this mode, exactly the same thing, except that the time at which it enters the horizon, well, I don't do it very well, but it's going to be closer to matter radiation equality. So K AH, because K is smaller. It's constant if you wish. Grow like the logarithm of A, and then grow like A. Okay? On all scales, growth is the same for dark matter. Now for neutrinos, you see where I'm going with this? It's not the case because of the sound speed, CS square of neutrino, which is, you would see if you do that correctly, that is basically given by this thermal velocity that I wrote down above over there, this ratio of pressure and this 3T over, so this is roughly equal to this ratio, which is roughly equal to, we said, 3T over M. Okay? So I should be careful. That's CS, sorry. I think that's CS. Okay, and so we can plug that in our expression for the Jinx length, which I erased, or did I write it down? Yes, it's it. Okay, you can plug that in this equation here to find basically what we call, well, sorry, you can define the Jinx length, sorry, you can define the Jinx length for the neutrinos, very good. And there's going to be a very important scale, which is the scale of the non-relativistic transition, which is precisely, so if we write it down explicitly for the neutrinos, we're going to get, 4 pi j a square rho bar over m square 90 nu square, okay? And we are going to define the, did I mess up? Why did I multiply by m? No. Did I mess up? Yes, I did mess up, of course. 19 nu square divided by 19 nu square times n square. Sorry. Okay? And we can define this. There's going to be a very important scale at which the ratios of mass and temperature is of order 1. That's this non-relativistic transition scale, which is defined as the moment where m is order 3 times t, such that this guy is of order 1. Okay? And that's our non-relativistic transition scale factor, sorry, scale, which we are going to see pop up in this equation. So K and R. So if you then, so you put that this is of order 1, this ratio gives you of order 1, so you have to just plug in expression for all these terms, and you find that numerically, non-relativistic scale is given by something like this. And you do things a little bit more carefully. Okay? So this means that depending on whether the scale is much, so if K is much smaller than NR or scale, this means that modes are going to behave on very large scales. The modes are going to behave just like dark matter. And on the opposite limit, so like neutrinos are dark matter. And on the opposite limit, neutrinos are free streaming, basically. Okay, and so the evolution for neutrinos is going to look like dark matter for a scale that's smaller than this guy. So like this, like this, like this. And for a scale that's greater than this guy, maybe like this. And then you're going to oscillate. And really, because they're free streaming, they are very quickly, actually, the term that I've ignored would be a lost term, and it would actually dump very quickly. So it's damped oscillation that are very quickly damped. I'm going to write damped oscillation because this is the solution that the equation we write, but really you should think that there's a lost term that makes it just decay away very quickly. Okay? And so you can imagine then that if you're if you're smaller or greater than this non-relativistic transition scale, is going to lead to this sort of suppression there that I've drawn. So we can try to go one step beyond, and actually, so we can derive an approximation for the modification to this growth function. So here I've done, I've done sort of a separate universe thing where I've just looked at, instead at the dark matter perturbation evolution, the neutrino perturbation evolution, but you can ask, what is the evolution of the total matter component? And the evolution of the total matter component, roughly speaking, now is going to be written by the same equation that we have written before. So we can write it as delta m plus 2h delta m dot, so with the friction term. Same with minus 4 pi g. And here, what we're going to do is we are going to remove the neutrino contribution from rho times rho. Okay? So the idea is that here, to get the matter contribution, matter, delta M is the sum of each component, delta CDM, the neutrino, etc. Should be a little bit careful with the rows that you're summing. And so you can schematically see that what's going to happen is that neutrinos are going to contribute to H here. Massive neutrinos in particular at late time are going to contribute to H. But on small scales, their densities perturbation are going to be removed, are going to disappear from this equation. Because they are experiencing this damped oscillation. So when you sum up their equation, basically they are going to be driven to zero, and the matter perturbation is going to receive this little penalty due to the fraction of neutrinos. And if you solve for that equation, you find that the solution of delta M now is proportional to A, still to A, but to the power of 1 minus 3/5 of F nu, where F nu should have defined is the ratio of omega nu over omega matter, or rho nu. I should say rho because this is time dependent. Well, no, actually it's today. Sorry. Yeah. Okay. And so this means that compared to a universe where neutrinos are massless, the growth of matter perturbation is suppressed by these factors. So, okay. So if F nu is very small, this guy goes to 1, this guy goes to 0, this goes to 1, and the ratio is equal to 1. But if this guy is non-zero because neutrinos are massive, then there is a little suppression in the growth of the matter perturbation. And then we can derive that the matter power spectrum is defined as the square of the average of this delta K is gonna scale like A to the minus, if you wish, 6/5 of F nu. So the famous results, and then you should, and then so which is this is an integrated result. Basically the matter power spectrum at z equals 0 is going to receive a suppression integrated, if you wish, over the scale factor from matter radiation equality, roughly. So if you were to plug in matter radiation equality for the size of the suppression, you'd be a little bit too large. The thing that's the famous result that you get, but these are just from fitting formula, you're fitting the suppressions to your result, is something like 1 minus, sorry, it's the delta, the ratios of the matter power spectrum in a universe where neutrinos are massive to the universe where neutrinos are massless is going to be something like, it's going to be 1 minus, and this 8 times F nu, that's going to show, that's coming from just fitting the equation, can be fitting the numerical result, can be understood if you basically, you take that A is order AEQ, the moment where, if you do that, you get, I think you get 10 F nu is what I could get. But it's just basically over time, since matter radiation equality, their growth is suppressed by a prefactor, and you get roughly this from fitting. Numerical simulation. Okay? And so now comes the thing that I've drawn above. And so when you look now at the difference between the matter power spectrum in a massive neutrino universe and a massless neutrino universe, normalized to this is the delta pk over pk. So this is centered around 0 here, as opposed to being centered around 1 because I've removed. I didn't adjust the ratio. There is a delta pk. You find this result that the amplitude at small scale of the suppression from fitting is about 8 f nu. From my simple approximation, you'd get 10. It's a little bit too big, but not too far. And also importantly, because of just how the free streaming scale, which I've now erased, it's below, is hidden, scale with the mass, you can find that the smaller the neutrino mass, the longer, the more velocity they get, and so the further away they free stream. And so you have a smaller amplitude of suppression for less massive neutrinos, but it affects larger scales. Did you get the idea? Complicated? Is it a bit too complicated?
This was also part of
yes, exactly. So using the notebook, you'd see that you could check. I comment. You could check these fitting formulas, this sort of things. That yeah, it was one of the things that are commented out on the notebook. Okay, but the basic idea that you need to remember is just that when we solve for the evolution equation of density fluctuation, we find that there is a scale that is important that appears. This is this Jinx scale. I erased it. I should probably have kept it somewhere. Yes, exactly. This Jinx scale. And for neutrinos, the sound speed associated with it is given by basically the ratio of the mass and the temperature. And at the time at which they transition, when the mass is of order of the temperature, this defines this non-relativistic transition scale, which we see imprinted in the suppression of the matter power spectrum. So that's it for the effect of massive neutrinos. And I can take questions here if there are, because I see a lot of skeptical faces. Or I can try and explain briefly the effect of N effective on the CMB. Please go ahead.
If you could explain the middle top graph for what, like the sum of the neutrino masses.
How did I go from that to that?
No, more. How will it affect it? Like, how will it look different depending on the sum of the neutrino masses? Can you see it from the graph? This
drawing.
This drawing.
Yes.
Okay. Can you tell from that drawing the combined masses of the neutrinos? Could you tell me how it shows up again? And you might have said it.
This is what this is. Like, this is the sum. Like, you should. Sorry. Sorry. I guess, yeah, my drawing. So if I put my neutrino, so I should put that. Here, the sum of the neutrino mass is equal to 0. Okay? That's the 0 line. I increase the mass of the neutrino. Now, the Gross equation that I have written down receives this little suppression. Instead of being delta m scales like A, I get that delta m scales like A to the minus 3/5 of their density. I take the square. I say, oh, let me look, since matter radiation equality, what is the accumulated effect? And you get roughly this sort of scaling, 8 times F. Okay? And if I increase the neutrino mass, the suppression increases, but the scale moves to the right because the Jinx length or the Jinx scale becomes greater and greater. The Jinx length becomes smaller and smaller. For dark matter, there is a Jinx length, but it's like all of the way here, because their temperature with respect to their mass is much smaller. And for neutrinos, their Jinx length, is somewhere. By the way, I haven't put it, but it's somewhere around. Well, yes, we said 0.01 or something like this. Okay. By the way, this is valid for warm dark matter, not only neutrino, anything. You can do it for warm dark matter. We can do it for anything. Okay. It's the same relations. Does that help?
Yes.
Awesome. All right. 10 minutes. Okay. I mean, yes, 15 minutes. Yeah. It's just, I think it's, you've seen most of the thing. We discussed most of the thing already. So what I'm going to skip is the impact of N effective on BBN, Big Bang nucleosynthesis, because that would require another half hour. And just to say it in words really briefly, the effect of N effective is to change the amount of helium. The main effect is to change the amount of helium, because N effective is very important in setting the competition between the weak interaction and the Hubble rate for BBN. The weak interaction and the Hubble rate. This relation that we had written, T has to be of order H. If you increase N effective, you're going to increase H. Then the temperature at which neutrino freeze out or escape is going to change, is going to increase. And that's going to change the equilibrium between neutrons and protons. And you're going to have more or less neutrons and protons, and therefore, sorry, more or less neutrons, really, because neutrons decay this time. And you're going to then end up having more or less helium. But I'm going to skip this part and just talk about N effective from the CMB, because currently these are the dominant bounds that we get. And really, this is the drawing that I had scaled here. I'm going to redo it here. What you need to know of the CMB in a crash course in 5 minutes is that there are 3 main scales in the CMB. Again, to really understand the physics of the CMB, you'd have to solve this delta G mu nu equal delta T mu nu, put in the perturbation of the photons, couple that to the other species, blah, blah, blah. But what you find out is that there are 3 main scales in the CMB. There is theta S, which we have already discussed, which is just telling you basically the position of the peaks. Okay, the frequency really in multiple space, it's the frequency of the peaks. And this is, just to write it again, this is the equivalent of the matter power spectrum. But for the temperature fluctuation, and since we observe it on the sphere, we use the multiple decomposition as opposed to a Fourier space decomposition. So theta S, if I change theta S, what I do, it's very simple. I just shift all the peaks by the same amount. We've seen that already yesterday. Okay? I don't know if you can see anything from my batch, but you just move the spectrum left and right if you change theta S. Then you have the scale of matter radiation equality, the angular scale, and it's an envelope. I'm trying to draw an envelope here, theta EQ, which comes from the effect that we've derived. Delta M grows basically during matter domination. That gives a very specific relation between the potential well that's going to affect delta T. The phi through the Poisson equation is going to be sourced by delta M, and phi is going to affect delta T in the end. And what you find is that based on matter radiation equality, fix how big the CMB power spectrum looks like. Okay? And the last effect, that's how big, how large the amplitude of the fluctuations are. And the last effect is a damping, which I briefly mentioned. Oops. This is called diffusion damping or Silk damping, after Joe Silk, who derived a version of that for baryons, where what's happening is that we are following a tightly coupled fluid where photons have a mean free path that's extremely, diffuse, or don't diffuse, because they're so tightly coupled, so their mean free path is very, very small compared to the Hubble distance, So at the beginning, very tightly coupled fluid, just because there is a ton of interaction. And as we get to recombination, which is the moment where precisely the photons can escape, that process is not instantaneous. We don't just suddenly escape. Suddenly, the photons realize that there is a little bit more space, if you wish. The mean free path of the photon become of order h. By definition, as we get close to AH minus 1, order. Okay? And that effect, the fact that it's not instantaneous, leads to a damping of the anisotropies. You can imagine that if instead of being tightly coupled, you start to diffuse, all the scales are going, the anisotropies on small scales are going to get erased by this diffusion process. Is the rough idea. You can actually write down an equation for it, like I'm giving you things with words, but you can really, using the same sort of logic that we followed, you can write down an equation that would tell you that there's a damping term. The 2H delta, would be, there's going to be a term coming from that process here that damps the temperature anisotropies. Okay, so all you need to know is that these three scales are core scales of CMB physics, in particular theta s. So of course I didn't write down their value, I should have, but theta s, which is this 1.0411, has been measured at, something like the fourth or the fifth digit. I'm going to make a mistake, but it's 0.1%. So, yes, sorry, that's 100 times theta s. So yes, it's been measured. I'm going to make a mistake here. I'm not going to be able to do that. Order 0.1% precision, okay? That's what I'm going to say. So all that matters is that this is super well measured. You never can mess up that scale, okay? The matter radiation equality scale, again, measured at the percent level. I forgot its value, but it's going to be a little bit smaller than that because matter radiation equality happens slightly before recombination, okay? Theta EQ, measured at 1%. And theta D, same thing. It involves the baryon density, and you know that the baryon density is measured at the 1% level, so it's going to be measured at the 1% level, okay? Roughly speaking. So N effective might mess up these three scales. And this is what I showed you already yesterday. What I showed you yesterday is if you just naively increase N effective, the main thing you do is that thing, and you don't even see the rest, but you're also messing up the rest. And then you can play with the cosmological parameter to compensate for those effects. Except you cannot compensate for everything at once. So what I want to derive is just briefly to tell you are the scaling relations between these things. So the sound horizon first, we wrote it many times. It's already over there. The sound horizon, that now is extremely important and is not fixed anymore because this thing that's integrated from early time, we said it doesn't matter because it's dominated by late time in the integral. The sound speed over dz h of z. Now the sound horizon might change because h of z receive a contribution from additional neutrinos. And at early time, this is all that matters. At z much greater than, at z greater than 1000 here, okay? So now if I boost the radiation density, I boost h of z, the sound horizon decreases, okay? And by the way, this is why, and you can compensate for that effect. I should write that. Let me be a little bit less sloppy than sometimes. So I'm going to write physical densities in this quantity. So here I'm going to write small omega radiation, small omega m, where omega radiation is equal to the fractional abundance times h squared, okay? So that's a fraction of radiation today. That's the physical density of radiation, okay? Because remind you that we've defined this omega as the ratios of rho radiation over rho critical today. And rho critical is equal to, let me not mess it up, 3 times m Planck square h naught square. So this is our normalization, okay? And here that h naught square is my h square, okay? Times 100. So when I go from capital omegas to small omegas, I'm just giving dimensionality to the problem. So I'm doing this because I don't want you to believe that H naught really appears here and I can just compensate things. What I want to show you is that here I'm increasing the physical densities of, I'm boosting rho and effect, rho in radiation. I'm boosting this guy, okay? And I hope, yes, I hope I didn't, yes, I think we're good. And to compensate now, I want to fix my scale So my scale theta is the sound horizon is now divided by the angular diameter distance, okay? And we already wrote that we can write this as h naught rs divided by the integral of that. So this guy is the integral of dz over, sorry, let me write one step, dz over h of z. Again, it's over there, so it's over there, times 1 over 1 plus z. And I can make h naught appear here. Integral of dz over what's called E of z, the shape of the expansion history, and a 1 plus z here. Okay? So now we see our correlation between the sound horizon. If the sound horizon decreases, I can increase the value of h naught. Okay? But I just wanted to say, be careful, it's not coming from that, because here really I'm changing the physical density of radiation. It was coming from the angular diameter distance correlation, okay? And this is why N effective is so interesting to solve the so-called Hubble tension. The Hubble tension is a difference between H naught, sorry, in lambda CDM, 67.5 plus or minus 0.5, something like this, exact numbers. It might be 0.3 plus or minus 0.3, but whatever. H naught versus the one that's measured by the Schuss collaboration. I won't go into details, but using calibrated supernovae, which has measured 73 plus or minus 1. Okay? And if that was the case, if that were the true value, you know, naively, without changing the model, you change completely this angular diameter distance, and the CMB would be completely messed up. So one way you can do that is by, by using this correlation. And so if you were to boost an effective in the early universe, which appears in the radiation density here, you know, I guess I could write it explicitly. It's going to be messy. Let me try. 1 plus 7, 8, 4 11s to the 4 third, and effective. Okay? Rho gamma. So if I boost an effective, I might decrease the sound horizon, which I can compensate with H naught. Okay? And the value that you find, if you wanted to reach that value, I'm telling you it's order 1. Fortunately, excluded because of those two remaining effects on the CMB. The fact that at the same time, all these angles are always given by ratios of some physical scale divided by the angular diameter distance. If I change the angular diameter, so yeah, if H naught increases, you would mess up the angular diameter distance. You have to compensate for it. But the scaling within the 3 quantities of N effective, so the physical scale that enters, N effective doesn't scale the same way the 3 scales. So this is what I want to show you now in the last 5 minutes. 5 minutes. Yeah. We are almost there. Honestly, we are almost there. It's really not that complicated to understand the rough idea. Okay. So what we've derived here is just really briefly that, you know, the sound horizon and H naught are correlated. If I increase an effective, I decrease my sound horizon, and I can compensate for that by changing with H naught. And when we played with the notebook yesterday, this is exactly what was happening. When we were requiring theta S to be fixed, the notebook for you automatically found the right values of H naught. Okay? And now you could ask, okay, well, I'm increasing H naught to 1. Would that also preserve these scalings? The angular diameter distance, so this scaling, now let's look at theta EQ. Theta EQ is the size of the Hubble horizon at matter radiation equality R or lambda EQ over dA. Okay? It's the same dA, huh? It's always the same dA that's going to appear. And the size of the Hubble horizon, as I said before, is roughly, again, we're doing roughly just to understand the scaling, AEQ HEQ minus 1. And you can see by dimensional analysis these sort of things. And because we're in cosmology, there's always an A, because you want to go from co-moving to physical, you know, that's the sort of thing. Okay, so we said now, how does my N effective affect those guys? Well, AQ I've already defined as omega radiation over omega matter. So this increases, obviously, if omega radiation increases. Okay? And we can compensate that. We can see that if I increase the matter density in the right amount, I can compensate and keep matter radiation equality fixed. Okay? And this is what we did yesterday. We had written that, so I can write that omega radiation, which is, again, this ratio here, you just plug in the numbers for that thing, and you get omega radiation scales like 1 plus 0.2271 NF. Okay? And 0.2271 is this guy. Sorry, omega gamma over omega matter. Okay? The right number here is standard model number is 3, you know, but you can put a larger one. So this is the prefactors that if you look at the notebook, you'd find prefactors like this. Okay? So what that means is simply if I scale omega, if I increase omega matter by that guy, you know, if omega matter goes to, so let's call this thing alpha. Omega matter goes to omega, so omega matter prime is equal to omega matter initial times alpha. I compensate the effect. Okay? And very good. And the fun thing is that from this equation, you see that omega radiation increased by alpha, omega matter increased by alpha, so h of z increased by, so h is proportional to square root of alpha. Okay, if I boost everything by alpha, all the densities by alpha, the h is proportional to square root of alpha. And so, what did I want to say? H naught Rs. So if I boost everything by square root of alpha, I'm getting lost. Sorry. My notes are not good enough. So what I want to say is that stay constant because you have the same, yeah, in the sound horizon here, yes. Sorry, so let me go one step further. Sorry, I'm going too fast. Omega matter is proportional to square root of alpha. Okay? But omega matter is equal to big capital omega m times h squared. Okay? So if I boost this guy by square root of alpha, and I don't want to mess up that guy, what it means is that h has to be proportional to square root of alpha, such that this guy stays the same. Okay? So h is h naught. That's h naught is proportional to square root of alpha. Okay? If I increase h naught proportionally to square root of alpha, while changing small omega m by square root of alpha, I'll be able to keep, I'll be able to keep this guy, no, what am I saying? Am I messing things up? I want to say that it has to be 1 over, right?
It's because omega is proportional to alpha, not to square root of alpha.
This guy is proportional to alpha?
Yeah.
Ah, yes, okay. Sorry. And so the bottom line is that there is a, I feel like I'm messing up the scaling. I'm sorry. That's the problem of doing things quickly on the board. The bottom line is that by scaling things by square root of alpha, but right now I'm messing up the scaling, this guy remains constant. So what I'm trying to say with my messing up the scaling right now, I'm sorry, is that the same scaling that allows you to keep matter radiation equality fixed allows you to keep the H naught times RS products fixed, okay? And I'm sorry, for some reason, right now I'm confused by this scaling here. Anyway, this is fixed, great, okay? So what we get is that by scaling things by H scales like square root of alpha, the omega matter scales like alpha. So what, everything is fixed. The problem now is now the problem now is this damping scale. This damping scale, again, is some damping, the diffusion damping scale divided by theta d. And what I want to say is that this guy turns out to be proportional to, not to square root of alpha, but to alpha to the, sorry. So it's, yeah, alpha to the 1/4. And the idea is just that because this damping scale, we can get from computing the mean, the mean scale, the mean length that over which photon diffuse. And this guy is equal to the number of scattering events times the mean free path square. That's just from diffusion coefficient calculation. And that mean free path here is equal to, is 1 over the scattering rate. And the scattering rate is the number of electrons times the Thomson scattering, C. Okay? And the number of scattering events is the scattering rate, so it's any sigma t, time the Hubble time. Again, there's going to be a h-1 here in this business. And so when we do this, we find that this guy is proportional to, so there's going to be some integral over conformal time time 1 yes, 1 over this guy, okay? And I can write this like this. And so you see that instead of having my square root of alpha, I'm going to get a square root of h of z that's going to appear here. So a 1/4. Okay? So that's the problem. I can rescale by the same square root of alpha. I can increase by increasing the matter density by alpha. Sorry, by alpha. I increase the matter density by alpha. I increase h by square root of alpha. I keep by my equality scale and my sound horizon scale the same, but theta d gets rescaled by alpha to the 1/4. Sorry, 1/4. Wait, 1/4. Yeah. Okay. Okay, so that means that in the end, we get the effect that I showed you before on the CMB sky, in the notebook. What we have seen is that so theta RD increases by alpha to the 1/4. Theta D increases by alpha to the 1/4. Okay. So LD, which is equal to pi over theta D, decreases by proportional to alpha to the -1/4. Yeah, proportional to alpha is complicated to write. Okay. Okay. It's like alpha to the -1/4. So it means that the length, the diffusion multiple becomes smaller. And so that means that a diffusion is going to translate as some exponential suppression square in our thing, in our CMB sky. CLs are proportional to this guy. So if this guy is smaller, it means that compared to a universe where delta CL, this guy is smaller, so it means that the suppression started earlier. And so that's why you get this sort of damping like that. Okay? So I can, yeah. This would be for n effective equals 3. We're centered around 0. And this, as I increase n effective, increase omega m proportional to scales like alpha, and h scales like square root of alpha. Okay. That's the idea. Okay? And so that, again, is why we are targeting the damping scale when we look at an effective with the next generation experiment. And that scale, again, we have so the damping scale is going to be a little bit smaller than the sound horizon because everything happens before recombination, okay? So it starts on fairly large scales, but most of the suppression, because it's an exponential, appears at a small scale. Okay? And from this, I can just conclude by saying what I had said at the beginning. The current constraints are an effective 2.86, I think, plus or minus 0.13 from Planck plus ACT, basically, which is something like this. Okay? Thank you for bearing with me until now. Sorry for messing up a little bit the scaling here, but you got the gist of it. Thank you.
Questions?
Hi.
Yes.
Yeah. So actually, you showed expression for Hubble constant, correlation between Hubble constant parameter and the
Yes.
sound horizon.
Yes.
So using that, we can measure the Hubble constant, right? So the left-hand side was the lambda CDM that comes from the basically large-scale observation, right?
Yes.
And the right-hand side, say the sound horizon comes from, I think, small-scale observation, right? Or
What do you mean by left-hand side and right-hand side here?
so basically, the left-hand side was theta s,
Yes.
and the right-hand side we had the sound horizon that
Yes.
comes from the BAO or something like that.
Yes.
And then there is Hubble parameter, so we can compute Hubble parameter using that.
Well,
So my question is,
yeah, the idea is that theta s, so what you're saying is theta s is equal to h naught rs divided by some integral
Yes.
that involves
yeah,
the density parameters.
yeah,
So theta s is measured in the sky from our maps. We measure it in the sky from the maps, from the correlation function. The sound horizon, we don't know intrinsically. We need a model. That's what lambda CDM gives us, or lambda CDM plus n effective gives us. Okay? We measure theta s, our model predicts the sound horizon, and therefore we get h naught. But by changing the sound horizon, the model that predicts the sound horizon, we can extract h naught. Currently, we don't have a direct measurement of the sound horizon.
okay, okay,
Okay? The BAO gives theta s. It depends on RS, but what we measure from the BAO is theta. It's always an angle in the sky.
And recently there were studies of measuring Hubble parameter independent of measurement of sound horizon. So could you briefly maybe just...
So I think what you have in mind is that there are, as I said, there are other scales in the CMB, theta D, theta EQ, and theta S. The main measurement of H naught is the measurement of H naught from the CMB currently is driven by the sound horizon because it is the thing that is better measured. But if you have access to the intrinsic size, if you use, so this is called the standard ruler. I said the sound horizon is standard ruler, but you could use, and I've erased it, but this one. If you had a model that tells you what is REQ, the matter radiations, the scale at matter radiation equality, the size of the universe matter radiation equality, if you had a model for that, you could find another way to get H naught. Okay. You measure that in the sky, your model gives you this, and you extract H naught from that. Okay?
Okay.
And the big debate is really, now is how to get that. Okay? And so people have, well, from the CMB, we can try to, you can try to find ways to remove, you try to erase, for instance, information on the wavelength, just to get information on the amplitude, to try to cross-check that you get the same numbers, things like this.
I see. Yeah. Thank you.
You're welcome.
Other questions? Okay, so then we thank Vivian again.
Thank you.